Alex Brooker here. Welcome to the second episode of the Travel Tech Podcast, and I have a treat for you. I just spent over an hour going really deep with James Dunthorne on all things drones, data, sensor networks, aviation, and AI. We talk about his PhD at university. We talk about flying a drone around the Houses of Parliament, over farmers' fields, and up and down railway tracks, and everything in between. So I really hope you enjoy this episode, and it's sponsored by Airside Labs, airsidelabs.com. So, James, good to see you.
Yeah, good to see you, Alex. So looking forward to this show and what kind of interesting conversations we might come up with. But really good to see you again. And let's talk all things aviation.
Absolutely, yeah. That sounds great. I'm really looking forward to this because I know you've got a really interesting background and story to tell that I think people will be really interested in. So what I was thinking, if you don't mind, perhaps start at the very beginning. I know you spent some time at university, and maybe that's where the passion for aviation began. But I was wondering if you maybe start us from the very beginning.
Yeah, sure. So I went to Loughborough University, and studied aerospace or aeronautical engineering, as they called it. It's actually part of the aeronautical and automotive engineering department because basically a plane is just an upside down car when you get up to sort of high performance vehicles. So it was really cool there. Yeah. Really enjoyed it. Yeah, you basically just got an upside down wing. So I think the Formula One guys and the sort of people building jet fighters are kind of similar, very, very similar skill sets, actually. But I was there and actually worked in the Loughborough University Centre for Autonomous Systems. So they have like a research lab at the university where you build drones, develop the algorithms, fly them around a room with like these infrared cameras in them, and develop these new control systems for
cool.
Whether it's landing on the back of a moving vehicle or trying to go and get them to autonomously land and things like this. So I really got into the drone space back in 2012, I think it was, around about 2011, 2012. Over 15 years ago now almost. So within that period, went on to do some research, so postgrad research, looking at collision avoidance systems for drones. So specifically looking at sort of, when you've got two aircraft flying towards each other, at what point are they no longer able to avoid each other anymore? We obviously get into collision scenarios, but actually modeling when a system can no longer actually produce a result is really interesting and important from a regulatory perspective and from a safety perspective. So that was kind of where I sort of started off, and then I went into the agricultural sector because apparently drones were going to be massive in agriculture. So we thought, okay, we'll do our own startup. We'll build this agricultural drone. We're launching it off these kind of catapult things and flying over crop fields. And we sort of had these cameras, these infrared cameras that we used to fit to them, and they'd be able to pick up sort of things like crop health. You can do things like NDVI, which is a technique you use to basically compare visible light and infrared light to be able to detect crop health.
What does that stand for?
Something differentiated index, vegetation differentiated index, or something like that. I'll have to Google it. But it's basically
that's close enough.
Basically, it works off the principle that a plant, say some wheat or barley, it absorbs visible light but reflects infrared light because it's too energetic for the plant to be able to use for photosynthesis. So a plant that's healthy will absorb a lot of natural light or visible light, but reflect a lot of infrared light. But when it starts dying or its health starts reducing, it starts reflecting more infrared light compared to visible. So you can see by looking at that ratio between visible and infrared, you can basically pick up the plant health. So that was going really well. Like we were making some really good progress, but the two problems we faced there was, well, how can you fly this thing long distance? Because the regulator said, well, 500 meters is your limit. And some fields, could be sort of 3-4 kilometers long. So
Much bigger than that, right?
yeah, so you don't end up having to do multiple takeoff points, and every time you're taking off and landing, that's actually probably about 50% of the work is doing the takeoffs and landing. So the more you can keep the aircraft in the air in one flight and cover a large area, the more efficient it becomes, and the price then drops down massively. So
Okay.
so yeah, that was kind of the major problem we found there. Along with the uptake of farmers was quite slow. They're not the fastest of people to
Right.
sort of onboard and uptake drone technology. But as I say, this was back in 2013, so drones had only been around a few years then. The regulatory environment was very early. It was
Yeah.
also, people were a little bit suspicious of these drones, think they're going to be spying on you or snooping on your activities. So we're in a very different environment back then. So I moved into an area called GIS, or Geographic Information Systems. If you're familiar with software or companies like Esri, for example, who make a lot of this software. And what it does is it's basically a way of think maps. It's basically maps, but with vector drawings and things drawn on top. And a lot of the work we were doing was around flood management, being able to measure the undulation of the land. So high points, low points. If it starts flooding, which areas would be fine, which areas wouldn't be. We did a lot of surveying work there. So land surveying, building surveying, and 3D modeling the environment, really, using that. And ends up one of the clients when I was working there was a company called Plowman Craven. I sort of ended up speaking to the managing director at Plowman Craven. They're a big, huge surveying company in the UK, over 100 people working for them. And they did some projects like, I don't know if you know, the restoration works on the House of Parliament, also did like Grenfell Tower, Tottenham Hotspur Football Club Stadium. So all of these big construction projects, they did all the surveying work, so measurement of that. And I sort of said, why are you guys not using drones yet? This seems like a really obvious solution for you. They also had a rail department as well. And I sort of said to them, like, I think we could replace what you're doing on the railways with drone technology. The problem was they needed like super high accuracies, like 5mm accuracy on the data, which is really hard to do from an aerial moving robot. But we managed to come up with a solution. We went for these medium format, high resolution, 100 megapixel cameras and built the system around that. And we scaled that department up to about 25 people. I think we did several million in revenue during that period as well, which went really, really well. And we got a lot of operational experience. I was sort of managing and guiding those operations and the drone technology that we were deploying out in the field. And then thought, well, I should probably do my own thing now. I've worked for other people and made them successful, but I'd love to do my own thing. And the big thorny problem back then was BVLOS drones. And if for those not familiar, BVLOS stands for Beyond Visual Line of Sight. So it kind of almost comes full circle back to my agricultural days where it was like, well, how do you fly further than the person can see? And the regulator said 500-meter limit. You can't go beyond that. So we were trying to come up with a solution around, okay, well, how can we enable things like drone delivery, long range inspections, or search and rescue missions and things like this. And so we built Neuron. So Neuron is we were deploying these ground-based sensors to detect air traffic and feed that directly into the drone systems that were flying. And the idea of this is that, the reason why the regulator won't let you fly beyond line of sight of the pilot is because if an aircraft comes along and it's on a trajectory with your drone, they've got no way to see each other, and so there's a risk of collision. So we thought, well, if we can provide the drone pilot with visibility of where all the aircraft are, then we can mitigate that risk, overcome the regulations. And at that time, I was working really closely with the regulator, writing these regulatory safety cases, sort of on the side as a consultant as I was developing this business.
Okay.
So we had a lot of drone operators coming to me saying, hey, I want to do this, but it's not within the rules. How do I apply for permission to do more than that? How do I fly a drone light show, a swarm of drones doing light shows? How do I fly this beyond line of sight in this specific area? And so I was literally working through the paperwork and the regulatory process with those operators. And so I was like, there's definitely an opportunity here to like provide a surveillance service into these drone operators and make that data available to basically flying robots. And since then we've been building. So that's kind of like the backstory, really. But yeah, going from sort of academia through to operations, and the technology behind that, the data around that, and also then the regulatory process as well. So it's been kind of very broad, but very interesting and fun at the same time. Managed to go and get to fly around Big Ben, which was quite cool. So I think I was the first person to 3D model Big Ben with a drone, and that ended up being used by the surveying company to create the CAD drawings for the House of Parliament. So that was really, really good fun. And you've done loads of really fun things, the Palace, Buckingham Palace, and at Grenfell Tower when they had the big fire. We went out there and were inspecting the building afterwards. So yeah, some quite interesting, high profile projects I was involved with directly and planned and flew and sort of orchestrated really. So yeah, it was good. It's been a good few years.
So it sounds fascinating, the sort of sheer level of flying and operations that you've led and coordinated. Dare I say it, before it was cool, sort of well before UK initiatives like Future of Flight happened around 2020. I'm really interested in your journey from doing the flying to recognizing the gap, perhaps to enable that beyond visual line of sight or different kinds of flying. And it sounds like you even started a company to help get it done overall, not just for yourself, but for the whole industry. So could you perhaps talk to me, how did you arrive at that epiphany to create Neuron and work on sensors in that way?
Yeah, so I think there was a few moments. So obviously right the way back to university days when I was researching collision avoidance systems for drones, it was obviously an up and coming area of research that was going to be of interest. And the key was how do we prove the safety of these systems? How do we build systems in a robust, scalable way where you don't have single points of failure? If someone goes online to watch their grandmother flying into Heathrow Airport, it's not going to take down your drone delivery system. So how do we come up with sort of this robust system, and how do we make sure that drones and aircraft can stay safely separated? So that was kind of like where I was sort of exploring the problem space. But then, I had real world encounters of the problems of not having these systems, which was in agriculture, having only being able to fly 500 meters. It was a huge pain in the backside. And, the aircraft was capable of flying kilometers, and I could see all of the airspace around the drone. And there was all of these problems that I was like, there must be an easy solution to this. And then also when we're, doing the network rail operations, when you're flying up and down railways, you're having to do them in short segments and then go to the next segment, do that one, and then go to the next segment and do that one. So it was highly inefficient. And I knew people who were working in this domain. It wasn't just my own personal experiences, but customers that I was working with on the regulatory side of things when I was consulting. I had people coming to me saying, look, I want to fly BVLOS in this area. Can you help me do it? And the way of doing it back then was, well, let's close down the airspace. And therefore, if we close down the airspace to other airspace users, then you can fly your drone in there. But that would take like 3 months to go and get the approvals to do it. You'd get about 3 months worth of operation when the airspace was closed. And then it would be back to normal again. And so you can't really build a scalable business model for all of these drone delivery, linear infrastructure inspection, search and rescue missions that all of these different customers I was working with wanted to do. So it was
so linear inspection is like the railway use case along a line inspecting, or power line.
Yeah,
search and rescue is
roads. Yeah,
search and rescue is like, okay, emergency situation, someone's lost on the side of Mount Snowdon. Where are they?
Yeah,
we can cover a bigger area much quicker than we otherwise could. So there's like a core, we can do it quicker and more efficiently if we use this technology, but then it comes up against a quite slow, perhaps understandably so in terms of the safety case, but
exactly
a big procedure to shut down the airspace to actually do the trials or whatever it is, do the flying.
Exactly. It was basically the only solution was what you would call a trial environment solution, where you could trial something out for a short period of time. But then it was like, right, okay, well, I've proven it all works. Now what? Can I operate? No, the airspace is now being opened back up again. So what we need to be able to do is how do we solve this problem in open airspace? If we ensure there's no traffic in the area, then obviously I can fly safely. As soon as there is mixed traffic in the area, then how do I fly safely? And it's pretty obvious. Well, you need to be able to see it. How do I see traffic when I'm on the road? I use my eyes to see it. But the problem with the drone is it doesn't have eyes as such, and the closing velocity of aircraft is quite high. So an aircraft looks very, very tiny on the horizon until the last few seconds until it hits you. So actually, even your eyesight, there was a study done by some airlines, I believe, a while ago, which sort of said some aviation people who basically said that really visual line of sight, a pilot's visual mitigation is almost meaningless. There's not a huge amount of benefit in doing so, and it's not actually that effective. I can't remember the exact number, but I think it was less than 50% effective. So even pilots, were struggling to be able to see with their own eyes. Could you make a machine to be able to do that, and to see, have a drone with a camera on it? Well, that's really hard to use cameras to detect aircraft. Like, it's possible on the bigger drones, I would say, probably, but on the smaller drones, certainly not. Not at that kind of distance anyway. Short range obstacles, you see these ones that fly through trees and avoid obstacles on the ground. It's a much different problem because you've got a lot slower closing velocity. But where you've got an aircraft maybe doing 100, 150 miles an hour towards you, it's closing at a very rapid rate, and so it only gets big at the last few seconds, at which point, based on the research I've been doing, it's generally too late by that stage. So you need to be able to see it when it's small on the horizon. And there's a few ways of doing that, one of which is using radars. These are generally really expensive to do. They basically emit a pulse, a sort of a pulse out into the environment and look for reflections of that pulse. The problem with that is they're incredibly expensive. They weigh quite a lot in terms of their mass, and ultimately, use quite a lot of power as well because they're emitting a lot of energy. So sticking this on a small drone and basically using up your available payload with the sensor that keeps everything sort of happy and sweet isn't really very useful. So what other solutions were there? Well, you've got electro-optical, so video cameras and things like this. But as we said, actually one of the pieces of research I did when I was back at the Loughborough University Centre for Autonomous Systems was looking at pixels and sort of saying, well, if I've got a video camera, how soon would I be able to detect an aircraft? And my conclusion was that, with a typical high definition camera, it doesn't even occupy a pixel until it gets very, very close to you. So simply being able to detect the aircraft in the first place would be incredibly difficult. You would need to have like lots of very high resolution cameras around you and, with a long zoom lens on them to be able to actually pick up these aircraft in enough detail to, first of all, not just know that it's there, but actually classify it. You need to, is it a plane? Is it a bird? Is it a balloon? Is it a cloud that I'm seeing? Or is it a speck of dust on my camera lens? There's a lot of variables there that makes it really hard actually to pick them out. So electro-optical wasn't really a complete solution. It probably has some space. It's certainly being used for obstacle detection on the ground, but not for aerial to aerial threats. So the other obvious one, which sort of stands out, is what they call electronic conspicuity. And so this is the principle that every aircraft has this transponder on board, the size of a pack of playing cards, I would say, and a little antenna, and you stick it on board your aircraft, and it basically transmits its GPS location. In most cases, it will have a GPS attached to it, and it will ping its registration number, its aircraft registration number, and its latitude, longitude, and altitude. And then other receivers can then pick that up. Now that's great. There you go, problem solved. If only it's that easy. And the unfortunate reality was that there are about 4 or 5 different types of transponder that exist out there in the market.
There's a range.
There's a range of them, and they're not interoperable. They don't speak the same language. They're on different broadcast frequencies. And so, you're not interested in seeing 20% of the aircraft in the sky. You want to see 100% or close to 100%. But how do you do that in an environment where it has mixed transponders? You also have the issue that not all aircraft are carrying these transponders. Hasn't been a mandate for these transponders yet, although there is talks of this happening very, very soon by the aviation regulators. So that's the key problem there is well, how do you have a sensor that can bring all of these things together? And also, how do you spot those legacy transponders? So, people have probably heard of something called ADS-B. It's quite a common transponder type, and it's on your commercial aircraft. So Boeing 737 and your Airbuses will all carry an ADS-B transponder. But you have had something before that, prior to ADS-B coming out, it's called Mode S. You actually had Mode C and Mode Alpha, I think, before that. But they're very legacy, those ones. But Mode S transponders, they tell you the call sign or the registration of the aircraft, but they don't have a GPS coordinate. So you only know that there is something out there with this call sign within range of you, because you're obviously receiving it, but you don't actually know where it is. So how do you detect those ones? They're the hard ones to detect, because yes, there is a way to detect them, but it's not straightforward. And the process you use for doing that is called multilateration. And for those who aren't familiar with that, you can think of it like triangulation. Basically, if you have, say, 4 or 5 sensors on the ground, what you can do is you can measure the time at which that signal was received from the air from each of these different sensors. And by having the differential between those times, you can basically pinpoint the position of the aircraft by triangulation. And that's what multilateration is in simple terms. But to do that, the processor of these sensors has to be really, really accurate on timing. You're talking sort of in the nanoseconds of accuracy. The timestamp needs to be, because for every nanosecond, light travels, RF signals travel about a foot. So, 100 nanoseconds is 100 feet of accuracy, is the way to think of it in a rule of thumb. So how do we actually go and pinpoint, how do we get that kind of accuracy? Well, the sensors need to be time synchronized with satellites or with an atomic clock of some description, to be able to correct that timestamp and to be able to sit on every data packet. So it was really complicated anyway. But what we did is we found a sensor that enabled us to detect all of these different types of transponders. So we partnered with a company called Jet Vision, sort of a leading company in the flight tracking space. And they made a sensor that detected all of these different types of aircraft, and it lives on the ground. You can't really do this from the air, because if you need 4 or 5 sensors to be able to triangulate the position, those sensors, you also need to know the location of those sensors. So if you've only got this sensor in your own vehicle, you can't triangulate the position because you've got one sensor. So you need multiple sensors, like an array of sensors on the ground, to be able to triangulate these positions. And that's why we came to the solution, which was that we needed some kind of ground-based sensor network to be able to pick up these aircraft. And
Right.
some really novel way of doing that. So
before we've gone deep, which is awesome, or high altitude, depending on your perspective. But before we talk about the data, the reason we need sensors on the ground is because of the variety of electronic conspicuity methods that are out there, and some air users don't have any at all. Balloons? Would somebody in a gyrocopter or a balloon, do they carry them sometimes? Sometimes, but not always.
Sometimes, and the thing is as well, if you're putting these things on board an aircraft, you're just adding weight to them.
It's weight,
And if you're having to detect 4 or 5 different types of transponder, you've got 4 or 5 different chips you need to have, maybe 2 or 3 different antennas you need to have. They may be interfering with your antennas that you have on the aircraft as well. If you're blasting out 868 megahertz and you're using 868 megahertz for your communications link, then you've got conflict there. So you don't really want to be putting all of this equipment on board your drone, which is meant to be lightweight. Lightweight things tend to fly better than heavy things. So you want to be avoiding putting too much equipment on your aircraft just for this on purpose.
So
you simply can't triangulate if you've only got one sensor anyway. So
exactly,
it's
so you can't excuse me, you can't have all the sensors on there for the electronic conspicuity. You can't use radar. Too many cameras, again, too heavy. And there's the physics of the resolution of, by the time you could see it, there's an issue. And then obviously conventional aviation right now uses air traffic controllers. They're the ones who give directions to pilots to change levels or do whatever. The pilots are not actually looking forward, working out and then communicating directly with each other. It is via a controlled service, right? So the way you've described where we seem to have ended up with drones avoiding each other is similar in that sense, in that having actually a separate controlling or at least informational service about where everybody is is actually the same way that we do it now with conventional flying, right?
Exactly, yeah. So commercial aircraft, are all being tracked using, at an airport, they'll have an expensive radar, which can be in the tens of millions of dollars, just to put one of these radars in an airport. And they will generally have a primary radar and a secondary radar, and also generally ADS-B equipment at the airport as well to pick up these electronic conspicuous aircraft. Now, commercial airliners are required to carry transponders. They're required to carry ADS-B transponders on board, and they fly in sort of semi-segregated airspace. I would say is like they fly in Class A and B airspace, which is separated from general aviation users. So you would have Class G is what most general aviation fly in. It's low down, generally away from airports and places like that. As soon as you start getting up higher, when you're flying at 35,000 feet on your holidays, you'll be in Class A airspace at that stage. And so when you're in those kinds of airspaces, then you have requirements to carry equipment on board your aircraft, and so all of these aircraft are conspicuous to each other, and they can stay safely separated because of that. In the lower airspace, you don't have that requirement to be conspicuous, and you've got all of these different transponder types. And so how do you pick up all of these different aircraft with different transponders? And how do you account for future transponder types as well? It's not just what do we have today. Like in Europe, EASA, SA, they basically are now introducing something called ADSL. Now it's very similar to FLARM, which is another one of these transponder types. It operates on 868 megahertz. Sorry,
is that UK only? FLARM, that's a slightly older technologies?
So FLARM has been around for over a decade. It's used primarily on gliders, so these sort of long gliders with long white wings, if you're familiar with them. But they are also used on general aviation aircraft, so little Cessnas, people who hobby fly and things as well. But they tend to fly quite low down. So if you're flying a drone, actually these kinds of aircraft are actually quite common within that airspace. You don't tend to see a 737 at 300 or 400 feet. Not very often, unless it's taking off or landing. So
not very close up, anyway.
Yeah, exactly. So you want to be able to see all of the aircraft that are within your airspace, and within that lower airspace volume, it's very mixed. There's different types of transponders, and not everything is still transponding, but it's not always necessarily a requirement for everything to be transponding. As long as you can meet the required safety levels, then that's generally acceptable.
So let's talk about some of the data involved, because I think you've articulated the problem. It's knowing where everyone is and then communicating that to everyone.
Yeah.
So how do you deal with the data? How does it work between the sensors, and in a sort of more general sense, how on earth does this stuff coordinate together?
Yeah, so we started off basically deploying some sensors around an area, a test area, where there's some drone activities and aviation activity. And we thought, well, let's just pull all of this into a data center cloud server, and we'll show it on a screen, and people can then buy access to this screen and use it to distribute their flights or to operate from. And the problem with that, though, is that when it fails, everyone loses visibility instantaneously. So across the board, every single customer who's plugged into that cloud system is now losing that. The other problem you get is, say, if a customer from America wants to have access to this data, well, the sensor data from America is being transported across the ocean to our server in the UK. And then the customer's then getting the data from our server in the UK and taking it all the way back to the US. So you've got these long hops of data going backwards and forwards. So what was the solution to that? Well, okay, we can stick a server in every country. And therefore it keeps the latency really low, keeps them highly performant, and keeps the data pinging backwards and forwards at real-time speeds. And that also solves some of the redundancy problem that everyone loses visibility at the same time. The problem comes is these servers aren't for free. You have to pay for them.
Mm-hmm.
So firstly, you're not getting much redundancy. If my UK server goes down, then everyone in the UK loses visibility of what's happening. You also end up with the situation where you end up with a much higher cost to these systems, because you're having to churn all of this data, and these sensors can generate about 2 gigabytes of data per day each. So when you're talking about thousands of sensors, you're talking terabytes worth of data processing. And not only that, but you also, need to do some other processing to it. So you might need to do multilateration processing, which is quite intensive as well. So you have all of these problems around scale of, firstly, how do you make a network that's robust and it's not, it fails locally, not globally? How do you keep latencies low so that you're getting real-time information to the pilot as and when they need it? A second or two can make a big difference if you're in a collision scenario. So you need to be able to see things in as real time as possible. And you also have this problem around, well, okay, if an operator needs to assure their operation and assure the systems that they're using, well, they would have to come to us and we would have to tell them how our system works. How does our algorithm work? And it goes through that whole process of how all of this fits together. So there's a lack of transparency around that. A lot of these systems would basically be like a black box. If you go to Flight Radar 24 or one of these other flight tracking networks, if you ask them,
other networks are available.
Yes, exactly. And you end up with all of these networks competing against each other. So
Yeah.
how do you actually, the problem space here isn't about how do we create a network, because there are networks out there already. The problem is that those networks, there's a lack of transparency, performance, and robustness to these systems. And regulators are not happy about us using fragile systems that have lots of latency. And there's actually requirements in a lot of the regulation that require it to be, less than 2 seconds worth of latency. We need to prove its availability, prove its performance and robustness, and all of these kinds of factors. And especially when you start getting up to national or international scale, those questions are just going to get harder and harder and harder, which is how, as soon as there's an incident and everyone loses visibility and you've got drones falling out the sky, because they've all lost surveillance capability. It's the equivalent of having a centralized network for all of the lights on the front of everyone's car. Imagine if everyone's driving down the motorway and then suddenly the server goes down and everyone's lights go off on the front of their car and in the dark. It's going to cause absolute chaos. So what you need is a system where, one person's lights can fail, and sometimes it happens, and sometimes somebody loses visibility. But you don't want everyone to lose visibility at the same time, because it creates a big problem. So just giving that context was, how do we stop the server from going down? How do we make it more robust? There's a few ways. We can create lots of servers and put them everywhere. But we've already discovered that that's quite expensive. It's also quite architecturally complicated. But I love the comment, which is, the best part is no part. So the best way to stop a server from failing is to remove the server from the network. If you've got a drone pilot or an end user who's consuming some data, then the quickest and safest way to go and get that data from the sensor into their platform is to connect them directly to each other with essentially like a long cable, but like an internet cable. And so how do we orchestrate a network of sensors so that any end user application can access those sensors directly? And that was basically the conclusion we came to, which was, how do we create a network where sensors and applications are on the same network and can orchestrate connections between those different nodes? And the common way of doing that is what they call an edge network. So an edge network is that very thing, is every node in the network is connected to every other node in the network, and they can communicate with each other, transact, stream data between each other. And the thing with that is, if a node gets eliminated, well, it doesn't affect any of the other nodes. It only affects the nodes that it's got that's directly servicing it. It doesn't affect the network as a whole. Whereas if you have this sort of hub and spoke model where you've got a centralized network, a centralized server in the middle, and all of the data coming in and then all of the data coming back out of it, you can imagine if you eliminate that, then you lost everything. So we went for that edge network design, and that's caused, that created a lot of other engineering problems that we had to solve. We went through that process. We basically we can think of it like a telephone directory. And that telephone directory is the way that all of these nodes in the network find each other, connect to each other, and then stream data with one another as well.
So if I could just take a step back, I'm trying to keep up with you and your explanation, because it's so fascinating and detailed. And I love the example of car headlights. So if everybody has the same subscription to headlights, and suddenly the server that's managing that goes down, then everyone's headlights switch off, is, I think, a really good analogy for the risks of like super centralization of that kind of service. And so what we're talking about when you say direct connection and one node being removed and the network can adapt, so that's similar to how the internet's designed now. So if one node goes down, you can still watch Netflix, might be slightly slower, might go via a different, as long as your connection's still there and you get to the backbone, you can still get to those other websites, those other servers over the internet, right? So you still the network adapts.
Exactly.
You can still get a connection. So what you're talking about is linking the consumer of the data directly with the sensor.
Exactly.
They need. Okay.
Yeah, and that's a really good example because the internet doesn't go down across the world. Your internet service provider may go down, and you might lose internet in your building, or even in your street, or something like this. But failures are localized there. Just because you lose the internet doesn't mean that someone on the other side of the country loses their internet as well. And so the internet is in itself like an edge network. It's connecting people in a point-to-point manner. And it has multiple routes through that network as well. If from a geography perspective, you have all of these sort of points within the internet that basically reroute data to the next point and to the next point. And if one point goes down, it just goes round them and goes through another route to the end user. And that's essentially similar kind of analogy to what we're doing. Is what we're doing is removing those sort of single points of failure within the network and making this more of a more robust, more highly available solution.
So why is that? I'm just going to sort of say the question out loud. But like, why would being hyper local at the edge be a good idea for drones operating at speed close to each other? Yeah. I think actually maybe it really is a better idea. It's a better way of doing it, right? Than having all the extra latency.
Well, if you think about it, a drone is operating in a very specific area. It's a real thing in the real world. It's got a location. It's got a GPS. Yeah. It's got lat long and altitude, and it's not interested in what's happening the other side of the world. It's interested in its surrounding environment. And so, how do you get that data from that local position to another local position? Do you send it to a server the other side of the world, or even the other side of the country, and then back again, or do you keep the data local to itself? And our view, and architecturally, it's been proven that it's a much more robust way to keep the data local. You keep the latencies really low for one. You're only for every for every hop you're doing, you're adding delay to the data, which is obviously not good. From a safety perspective, you want real time, as real time as you can get, really. You also don't want, there's a lot of people that use these flight tracking applications like Flight Radar 24. And, if there's something really interesting happened in the world.
Plane Finder.
Yeah, exactly. There's
all that and others. Yeah.
So there's several of these networks now, but when someone goes online and say the Queen or the King comes in to land somewhere, or there's an incident somewhere in the world, a plane goes missing or there's a plane crash, everyone hops on these systems and starts looking at it, and puts a lot of strain on these servers. So what you don't want is someone else's operation or use case to influence the safety of your own. You want them to be independently managed and to not have this kind of dependency on someone else's operation, because ultimately you want these things to be on all the time and working all the time. So how do you disintermediate all of these things? And so what we did is develop this architecture which enables you to have low latency, to have a robust network which localizes failure, and ultimately keeps data close to the source, which is what you want. It's the same for airports. Airports are interested in their surrounding environment, so there's no need to send it, over to the other side of the world. But what we did see, certainly in the early 2000s, was this kind of movement towards SaaS. sort of SaaS architectures.
Software as a service.
Exactly. And this
subscription model.
This became a really big thing, in the early 2000s. And I think that's how a lot of these flight tracking networks evolved. They're like, well, let's do a flight tracking SaaS. Let's pull everything into our SaaS, and then people can come to our software. We provide it as a service and sell a subscription to them. Which works for, some cases for where you're looking at analytics and things like this. But as you start scaling these more safety critical systems, how do you get to that next level of reliability where regulators feel comfortable, they can sign off on things, and you can provide data in an assured way that's predictable and doesn't have all of these sort of bottlenecks associated with other users flooding the network, or servers going down and everyone losing visibility at the same time, or I don't know, there's more use of a particular network and suddenly the latency increases to 10 seconds because now you've got more traffic and more users on the network. So how do you reduce all of those dependencies? And this is basically our way of solving that.
Is it also a potential cyber risk if one part of the network were to come under attack, or even some sort of sophisticated denial of service? We're seeing a lot more spoofing, both GPS, GNSS jamming and ADSB spoofing these days. Is that's all? I mean, you're sort of enthusiastically nodding, but is that part of the issue as well? Would that affect your architecture in a different way, or
precisely?
Or not?
Yeah, so there's two elements to cyber risk that needs to be considered. It's firstly the centralization of the data, because if you have the single point of failure, and there's lots of ways it can fail. One can be a mistake that we've made, a bug that we've captured. It could be the actual hardware itself, or the power, internet access to that server, or it could be a malicious attack. Aviation systems are safety critical systems, and in periods where there is tension between countries, there's obviously a few of them around at the moment. People may not want you to see where aircraft are for whatever reason, or they may want to cause disruption to your country or your operations. And if that happens, then you've got a gold mine of information that if you can wipe that out with a denial of service attack, for example, then you're in a tricky situation. And yes, there's always countermeasures to all these cyber attacks, but then there's always counters to these counters. So you end up with this sort of, this kind of cat and mouse situation with cyber where, you're always constantly creating patches, and then they're creating new ways to exploit it. And then you're creating patches for those, and then they're finding new ways to exploit that. And so there's never really any final solution to that. There's ways you can mitigate it, but if someone wants to try hard enough, then they'll find a way to be able to generally go and shut you down. And you see it, I forget who it was, AWS, I think, had outage recently. So I don't know whether that was cyber or what was the reason for it, but there was certainly some kind of bug or software issue. I think they committed something they shouldn't have. But yeah, these systems do go down, even though AWS and many of these products that are out there lost availability, and people couldn't log into their accounts because AWS was down. Can we accept that as a piece of infrastructure for aviation, or should we really be building something that's more robust to that kind of failure mode? And our view was our view was the latter. So,
well, I mean, the hyperscalers, every couple of years there's a big outage, I think, ever since I've been involved in tech. And it was Cloudflare. Within the last 12 months, they had a massive issue that took down a third of the internet. I couldn't log in and check my LinkedIn comments for a few hours. It was very distressing. But you're right to to flag that as a different approach. So let's bring it. We've gone deep technically in terms of the sensors and sort of the motivation behind why you've started and built the company, and then we've talked about why and how the data can be brought together with the advantages of your approach and the architecture. So what are you up to now? Like, what's the so where are you up to, and how are things going? And let's sort of looking forward, perhaps what's coming up on the horizon.
Yeah, so right now we did a lot. It was quite a deep tech problem. This, as you probably heard, this isn't a dog walking business or anything simple like that. I do sometimes wonder whether I should have gone for a dog walking business. It'd be a lot easier, but probably wouldn't have been as excited about the idea. But
once AI takes over, plumbing, electrician, dog walking.
Exactly, they're probably great business now.
We might all be out there. Yeah.
But,
sorry, go on. Go ahead.
But yeah, right. So around about 18 months ago, we started selling these sensors through JetVision. So we basically partnered with JetVision, this flight tracking manufacturer. And we deployed our software onto their sensors. So they came basically out the factory with our software pre-installed. And we started selling them. So we were just running a beta program with some community members who wanted to buy a sensor, install it on their property, and share their data with the network. And the aim, why would they do that? Well, the idea is we provide them with a revenue share. So the business model we came up with is, how do we actually scale this network? And that's the biggest challenge, with any network business, is how do you scale it? What's the incentive for people to do this? Are we going to install, all of these sensors ourselves by flying around the world? Right, that might be great if you're addicted to traveling, but probably needs quite a lot of capital to do that. Quite a lot of investment capital to do that. And the problem then comes is, well, if something goes wrong with a sensor, you then need to maintain it. So we then need to fly out every time a sensor goes down and replace it with a new one. And actually, what's the better way to do that? Is it better to do it all yourself, or actually the people who live in the properties where the sensors are going? Why not get them to do it? Why not the best person to maintain the sensor is the person who's closest to it? So what we did is we started selling the sensors to scale the network, and that went quite well. We sold around about 90 to 100 sensors, I think, quite early on in the first couple of months, and then we sort of just paused it there and go and catch up with the tech stack and make sure that was working right. And then recently, in the last few months, we've just launched with a global distributor who's now selling, I think this month, in the first 3 weeks, they sold about 250 sensors. The first batch of 200 sold out in literally 10 minutes. So people are really excited about the project and want to be involved with this infrastructure. They want to help contribute to it, and they're excited about the opportunity to earn some passive income from their sensors. So that's been really, really good. And then we've been working on the customer side as well. So the customers, throughout the last several years, we've been working very, very closely with some big players in the aerospace department, the UK regulator, with a lot of drone companies. And we're now taking that from POCs now to operationalizing it. So at the moment, we're focused on sort of small scale operations. So operations in local areas, not national scale quite yet, or global scale. So on national scale, you're looking at sort of the big ANSPs that are interested, the regulators and governments and people like that, and maybe even sort of security intelligence. And even the police forces at a national level. At an international level, global level, you've got insurance companies who are interested in this kind of data. You've got airlines who want access to this data. And and a few other parties like media companies and again, sort of defense companies and security companies. But, since we weren't at a global scale or even a national scale at that stage, we opted, okay, the first thing we can do is look at local operations. So an operation around an airport or a drone operation, or maybe even a security operation around within a city or around a sporting event and things like this. And so that's where we've been focused at the moment. So we're currently talking to a range of customers. We've already done loads of integrations with software partners, so drone OEMs, and we've got built actually open source flight information display, which is really cool. So I think it's the first open source flight information display out there, and is currently live and operational in an airport down in the southwest of the UK called Land's End. And I was actually talking to a guy the other day, and he was like saying that apparently some of the biggest IT cyber challenges were actually solved on the Isles of Scilly many decades ago. I forget what it was he was talking about. There was some cyber challenge. I think it was to do with latitude. That no one could work out how to measure latitude. Is it latitude or longitude? And they solved that down there apparently. So yeah, we're operating and solving a new challenge in the same area, which is quite interesting.
Yeah, longitude's the hard one, isn't it?
Longitude. Yeah,
longitude's the harder one. So I just wanted to say, so it's really interesting the way you describe it. I think because the way that you've articulated your differentiators, working locally actually plays to your strengths with a low latency, direct connection. You don't need global. You don't need global coverage. You don't just start with global coverage.
Yeah.
You're targeting specific use cases in a physically close area.
Exactly.
And then using those direct connections, low latency approach to solve problems for a specific region or mission or situation, right?
Precisely. Yeah. And the thing is, as you scale those local operations, you end up with all of these puddles forming bigger puddles, and then those bigger puddles forming lakes, and then those lakes forming oceans. And then you slowly can go and get this like global coverage just from the addition of these smaller puddles that you're building. And when I say puddles, I mean coverage within your network. So you can build up these little coverage areas, and sell those into various different customers and provide them with that sort of independent high assurance, low latency data that they need to be able to meet regulatory requirements. And without that, they simply can't fly. They're not allowed to fly by the regulators. So it's a real, painkiller to their problem. It's a big problem they have, because ultimately these companies, if they can't get to that point and have that kind of data within their systems and be able to see this information, they're going to go out of business. So it is literally an existential problem for them. So by tackling this very problem and being focused on a scalable, robust solution for the future that regulators have already looked over and have already given their sort of initial approvals on and happy with, that basically puts us in a really, really sort of unique position, I think. And when we've obviously talked about aviation a lot, but there is scope for this to go way beyond aviation. Like what we're talking about is a new type of network, really. And our team quickly realized that actually, whether I'm plugging in a flight tracking sensor or a weather sensor or maybe a GPS sensor, or even a car into this network, what you're talking about is really a new IT infrastructure that can connect disparate IoT devices, let's call them, and making that data available to software applications. And software applications today are AI and robots. That's the future. That they are the future applications. I think pretty much every SaaS has a AI component in it now. As a minimum, it's got an AI chatbot. But there is, there's a lot of use cases now are going to be AI first. And how do AI and robots really understand the physical world? if they can't access the data from them. So,
well, I wanted to, that's what I wanted to come to next, really, because a lot of the, I suppose, constraints that we've talked about with drones needing to be not just lighter than air, but not overloaded with cameras and lenses and sensors of all different shapes and sizes. Those are physical constraints. Those are, and the latency needs that we've talked about are derived from how close some of those sensors are physically. So, excuse me, given that AI, some people say is useless, doesn't understand the real world at all. Some people say it's amazing, incredible, and it could do everything. It's going to take over. What's your view on AI? Is it a tool that you're using yourself as a CEO founder with your teams, and you must have a team of engineers? Are you using AI in your company as a tool? And what's your view on AI in the product as well?
Yeah. So yeah, pretty much every one of our team is using AI now in everything we do. Even in our financial systems, our monitors for our financial systems are vibe coded. Our head of finance was like, I don't really like the software that's out there. I want to just create my own interface so I can see all the key information that I need in one heads-up display. And it took him a couple of days to build it. But the thing is, now with AI, you can build anything you want, and anyone can build anything they want, which is an insane time to live in. I personally, I never really built much software myself. I was more of an systems engineer level. I did a bit of coding, MATLAB and Arduinos, and a little bit of sort of C and stuff like this. But it was very minimal. I'd never pretend to be a experienced software engineer. But now with these AI tools, I know we were behind on one of our KPIs a few months ago, and we needed to make up time, and I sort of offered to help out, and I was able to help out just as much as the engineers were, just because if you understand the engineering of it, you don't need to understand necessarily how to code, but you just need to know how to architect things. You need to know what a database is. You need to know what an API is. You need to know what authentication is, and keys, and tokens, and all of these kinds of things that you use in software. If you can understand all of those elements, and caches, and what they're used for, and why you would use them, when you would use them, and how to build an algorithm, the software, the building the software bit is a lot easier now. So software is no longer really a moat anymore. Always used to be, well, if you had complicated software, that was your moat. You'd patent it or try and patent it. Certainly wouldn't be giving the source code away to anyone else. But nowadays, it's not the same anymore. It's people can turn ideas into reality very, very quickly. So yeah, we use it all the time within the business, not just for coding, but for written work. We do, sense checking. You can write something out and then give it to AI, and then you look at it afterwards. It's like, wow, this is so much better than I would have written it. So it can neaten up, things that you're talking about, your marketing materials. Our head of marketing is using sort of general or generative AI for creating videos and images. It's good for like decks and presentations if you want to create images for those, and you're not going to fall foul of like copyright issues and things like this. So there's tons of things that we're using it for, but similarly, we're using it in our business. We've actually got a core component of the product that's using AI and is going to increase its use of AI over time, because we've basically got a data network that for the physical world. We're plugging in currently flight tracking sensors, but we're talking to OEM partners to plug in other types of sensors as well. And to sort of build up this global network of IoT devices that are sensing the real world. That raw data and providing that data to customers is valuable, but there's also a value add we can place on top. So you kind of look at this sort of like buyer on one side and seller on the other side. And in the middle, you got the network that sort of pushes data backwards and forwards. But on top of that, we're building a platform which is going to have an AI brain to it. It's be able to make sense of this data, provide sort of like higher value insight, I guess, into that fused picture of the real world, so that you can ask it questions and it can tell you what's happening. You can use things like MCPs to be able to talk to this network and to understand the what's happening out there. So, if you want to know when a plane's going to come into land, you could ask this platform, this AI brain, to basically tell you. It'll tell you exactly where the plane is now and how long it's likely to take before it lands. So these kind of things, without those kind of connections into the real world physical devices, it's got no chance of being able to answer those questions. The digital world is fine. The digital world, AI is very, very competent with, but for the physical world, it's not so much. But I probably share. I've got a very, very optimistic view of how AI and robots are going to affect the world. I think, and I heard a quote yesterday, I think it was, which made me laugh, and I think it's a fantastic, best quote I've heard for a long time, which was, "It's better to be optimistic and wrong than pessimistic and right." So I quite like that one. So yeah, it's better to be optimistic, and maybe it's not quite as optimistic as you think, than to be pessimistic and wrong and right. Sorry. So I think when it comes to AI, I think we're going to see the biggest change that generations have seen. We're already seeing it today. There'll be some positive things about that. There'll be some negative things. It's going to cause a lot of disruption to the job markets, I think. You're going to see a lot of sort of less skilled jobs being replaced with AI, but that's going to create newer jobs. There's going to be other jobs that will replace it, like there was with, we went from the horse to the car. It will happen when we go from our current systems to these sort of future AI generated systems. So I think all in all, I think the future's looking very strong. I think we're going to reach a point where there is, worldwide abundance for a lot of things. So you can have whatever you want and when you want. And that might take a while. It's not going to be in the next couple of years. That might take 15, 20 years or so for that reality to be hit. But if you just follow the trends, things are getting cheaper. Software is cheaper to build. Once you then integrate AI with robots, then houses get cheaper to build because now the robots are building them. So what's the cost of anything? What does the cost become? The cost becomes power, the power cost. If the input for all these AI and robotic systems is power. And so when you've got these things being built with AI, then ultimately your only input into that system is power. And robots can build huge solar farms. They could mine, the materials needed to build these solar farms. And you can start seeing sort of like this aggregating effect where the more automation comes in, the quicker and quicker and quicker things become automated. And so it's they call it the singularity for a reason. And when I'm sort of seeing the speed at which these different systems are now developing at, you're seeing it in action. The singularity is kind of real. It's accelerating at one hell of a rate. Now there will be a lot of industries, I think, where AI takes longer. And I think actually aviation is one of them, because you're talking about something that's safety critical. It's generally worked on assurance and certification processes, which doesn't just require it to be built, it requires it to be proven to be built correctly, and for it to be safe. But AI will have a part in that as well. In the assurance process, I feel that AI is going to reduce the time to assure these systems. Testing processes, it's very good at doing repetitive tasks. AI is great at doing those things. So I think some of those will get resolved as well. But actually, what will be the biggest blocker, I think, is the public. Is like, how will people accept robots being around everywhere? Will people want a humanoid robot in their home, for example? And what
I think some will, won't they? But there'll be a backlash for sure.
Exactly. Yeah. So there's going to be I think the resistance is going to be coming from that robot took my job kind of almost type scenario, or these things aren't safe. That robot, hit my child, or it might have been accidental or whatever, but injured my child for whatever reason. So you're going to start getting that backlash, I think, which is going to make people think, okay, let's slow this down a little bit. But will we be? I guess the question will be, will we be able to slow it down at that stage? And that's, I think, the worry of some big leaders in the AI field at the moment about the safety of the technology.
So there's a lot in there. A lot that we've covered. This is a travel tech podcast, and we could stay on a lot of aviation stuff and gone super deep. But perhaps we can bring it round. So to travel, do you think? And this follows on a theme from the episode last week, where there was a big discussion about AI taking over and helping knowledge workers be more efficient and effective, but also increasing the value of face-to-face meetings. So do you think that we will travel less or travel more in the future once AI has improved, even beyond what it can do already?
That's a really good question. I think more. I think more, because I think we'll have a lot more time. I don't think we'll be working as many hours. I think,
or working at all,
or yeah. So, what else will we have to do? Travel. And you see people like SpaceX talking about 30-minute flight, across the world, using their reusable rockets. Sounds crazy. I'm not sure I want to be the first person on there, but I think we're going to start seeing travel times reducing. I'm going to see more efficiency in the transportation sector. Just things like air taxis, for example, something that have been on the horizon for a while, and still a lot of work to do before we see them flying routinely. There already are, I guess, air taxis out there. They're called helicopters, but bringing that price down for the everyday person. That's going to increase and improve travel for everyone. If I want to go down to Cornwall from London, for example, that's quite a long journey. You have to get on the train and then get buses or hire a car, and you're generally talking about multimodal transport for a lot of these places, especially sort of less connected places. So I think we're going to see those barriers and those inefficiencies reduce over time. But I think people will spend more time in person, because I think it's going to become more. There's going to be a lot more emphasis on things like the arts, probably. Things that are more creative and fun, entertainment, spending time with each other and things like this. That's if the AI and robots don't kill us all first. But I think, I do think that in-person time is becoming. It's weird that the more digital we've got, the more we value in face-to-face time. It's quite interesting, that sort of dynamic.
I think the argument being, if everybody can ask ChatGPT or Claude or Le Chat for a perfect slide deck or the perfect white paper, or go to Lovable or V0 get a beautiful website just from a prompt, then if you're the consumer of that product, then if everyone has a perfect pitch, if every slide deck is perfect, then how do you differentiate? And it could be that it does come back to, oh, well, I went to university with that person 25 years ago, or I worked with them on a previous project. It comes back to personal connections.
Yeah, and I
rather
think
than
the underlying
digital
factor behind that is trust, ultimately, I think. Because, whenever you buy something from someone, generally what you're doing is you're working out whether you can trust them or not. Do you trust that if they don't perform or they miss whatever they're meant to be doing, that they're going to work their socks off to put it right? Are you sure that they're actually going to deliver to a high quality? Are you sure they're going to, be the right investment for you? Or are you sure you want to be their friend? There's lots of things, but I think ultimately it comes down to trust. Is when you're operating digitally, there is no way to kind of get a gut feel for whether that person is somebody who has the same values and morals that you might have. So I think when you meet someone face to face, you kind of understand people's values better, and work out whether that's the right kind of partner for you with whatever it is you're doing. So yeah, I think. So I think you've got two trends there, is that people are going to trust each other less as AI increases. You've got a situation now where you're watching videos on social media and you're like, is that real or is that AI? And you're getting tons of these now, and some, like, you're just about able to figure it out. At the moment. You give it 2 more years and you won't know the difference between the two anymore. It'd be impossible to tell from a video. I saw some interesting ones.
I agree.
Where they go into go into a clothes store and they take a photo of someone while they're in the clothes store and then generate a video of a husband kissing some other woman, and then show it to the wife and say, "Look, did you see this?" And that, the wife is distraught because she's seeing a video in real time of her husband essentially kissing someone else in the store that they're in now. And he's like, "Well, that wasn't me." It's like, "Well, it clearly was. Look at the video." And it's crazy that how you could
wild
already trick people with it. So you can't trust video anymore. You can't trust images anymore. You can't trust text anymore. If you ask someone to give you their CV, is it their CV or is it the AI's version of their CV? So you can't really trust really digital content anymore because it's generally AI doing most of the heavy lifting a lot of the time. So that's one trend. And sort of the other trend is around, people having essentially more time on their hands. So, the less work AI that we have to do and AI does for us, then ultimately the less we need to work. So we'll have more time to spend with each other, and we won't be able to trust each other online anymore. So we'll have to meet up in person. So I think it's a trend that's almost inevitable, really.
I think we'll see how it plays out, because I think the advent of computers was supposed to give us much more leisure time, and everyone just ended up working the same, if not more, and producing more, and so expectations go up.
Very possible
in sort of tandem with the technology. But this has been fantastic and awesome conversation, James. Is there anything coming up in the next few months you want to share, perhaps for people who are interested in looking up Neuron and seeing what you're up to?
Yeah, so people can see sort of keep up to date with us. It's neuron.world on the internet, and it's neuron_world if you're on X or Twitter as it used to be called. But you can follow a lot of the stuff we're doing on there. We recently won a project with NATO, which was really, really interesting. obviously, robust, secure, cyber secure infrastructure is of interest to governments and the defense industry. And so what we've seen is that our solution is not just a commercial application, but also a defense application, and has a lot of dual use cases here. The one that immediately springs to mind is tracking drones and understanding where they are in the battle space, because they're not using, you haven't got people running at each other with swords anymore. It's you got them sort of flying these little machines at each other now, and that's it's well, I've tried to not look at too much of it as I can, but being able to detect those early and protect troops, protect the front line from any harm is obviously an area that's important in defense, but also for security, around airports and things like this. We saw what happened with Gatwick. There was a huge market there around airspace security. So airspace security and defense is an area that we're seeing increasing amounts of traction from, and it's in particular, with the airports as well. The business case for airports is not as strong as it is for drones, because they generally have a solution in place today. It might be inefficient, it might be really antiquated and old. They might not be able to allow drones to fly within their airspace perimeter, but that's not as big a sell into the airports as it is for the drone operators who need it to be able to exist. So drone operators have a huge existence problem that they need to solve.
Okay.
Airports don't have that as much. So how do we improve that value proposition for airports? And the idea is we're now doing some work with drone detection sensors. So being able to see, we talked about transponders being on these aircraft, but actually some of these drones, they don't have transponders on them at all, but they do have a RF signature because they're communicating with the pilot on the ground somehow. So you can pick up these RF transmissions from the drone and then relay that into an airport. So if there's a drone flying at the end of Heathrow runway, then they can see it and they can detect it and do something about it. So we're seeing a lot of improved interest in that sort of security market as well, and working with OEMs. So some of the testing and evaluation we're doing over the next few months is going to be around integrating these additional types of sensors into this environment for security, airspace security purposes, and also in the future defense purposes, for defense reasons. So that's probably one of the biggest pieces of news. We've obviously got the global distributor for sensors now set up, so they're selling like hotcakes. They can't sort of build them quick enough at the moment, so that's the problem now. Just supply chain problems of being able to produce the volumes fast enough. Luckily, that's not our problem; that's our partner's problem. But obviously, that has an effect. We can help and try and improve that process with them by giving them good, forecasts and maybe dipping a bit of capital into it as well, just to sort of reduce the lead times on the products. But yeah, that's basically some of the key pieces. And obviously at the moment, talking to different partners and trying to find, who has the best problems to solve within the drone sector at the moment. So, working with a lot of drone operators and talking to them and trying to basically setting up sort of operational capabilities at the moment. So that's sort of our focus. But I think that's probably it for the moment. I could talk for another 3 hours, I'm sure, but I think all your viewers will be asleep if I go on for much longer.
No, it's been absolutely fascinating, James. Thank you so much. Just love hearing the depth and complexity behind some of these things, in particular that journey of working out how do you try and solve this problem. You can't put the heavy thing on the little drone, you can only do it this way, you can't use that sensor, and so by process of elimination we've ended up, and we have a really interesting and differentiated approach, which has been awesome to learn about. And thanks again. And it's been brilliant.
Really enjoyed it. So, but yeah, thanks for inviting me on here, and yeah, I'm excited to see the live version. Hopefully, it's not been edited up to make me say something completely different to what I actually said. But I think I fully trust you on that. But yeah, no, it's really been really fun, and I was if you ever want me to come back and give you updates in the future, then feel free to give me the nod, and I'm happy to hop on here and come to the Alex Rogan experience.
Thanks, man. And yeah, sponsored by Airside Labs, airsidelabs.com.
Exactly.
And subscribe. Yeah. All right.
But love the work you're doing. Like, I obviously known you since you were back at Snowflake, and then went on to Sirium, and doing some really, really cool work there. And obviously did quite well through that process. And yeah, I'm excited to see what your sort of next big thing is going to be, because I see you doing a lot of stuff with AI and testing of AI and things like this. You sort of got your fingers in a few little areas at the moment, so it's going to be exciting to see that progress and how that sort of works out. Are you sort of kind of feeling your way along that journey at the moment, or you have any kind of plan yet, or are you just kind of seeing which way the wind blows?
You're turning the tables on me, James. It's not supposed to ask me questions. No, it's all good. It's all good. I'm solopreneur and learning AI, building AI, building AI systems and chatbots, and working with awesome startups, and doing lots of cool things. Let's see how far I can go as a solopreneur and not have any humans other than myself. Although I've learned that context switching is that's the real bottleneck there.
It's hard, isn't it?
The brain context switching there's only so many instances of Claude code I can have in terminals across my display before I literally can't cope.
So you've got your workbench with about 40 machines all coding simultaneously for you. Yeah.
No, that would be insane. But there's some really cool automation stuff that's coming out soon.
Definitely.
Yeah. No. Thanks again, James. All good.
Yeah. Best of luck with the podcast, and look forward to seeing it going live. And if anyone wants to get in touch, obviously they can get in contact at neuron.world, and there's links on there to contact us if you want to send a message and find out a bit more. Then check it out. And if you want to track some planes in 3D, then 4dsky.com is the one. There's you can get in there, click on the map at the top right, and you'll be able to see like a really futuristic view of the airspace, which is kind of cool. And there's some new releases coming out in the next few weeks, so that's going to be really cool. And going to be some exciting new features in there. So none of this boring 2D map display, but we're going 3D, and as the name suggests, eventually 4D as well with time, so be able to rewind. We haven't worked out whether you can fast forward yet, but you can certainly rewind. But yeah, it's going to be really fun, and excited what the next 12 months will bring. But yeah, thanks very much for inviting me on, Alex, and good to see you again as always. And hopefully have some more exciting updates for you in the future.
No, love it. Thank you so much, and all the best for this year. I know you and the team are going to smash it. So good stuff, James.
Nice one. Cheers, Alex.